Okay, I think we can start. So I'll start with recalling what was done previously. I ended at the list type, at the homogeneous lists, and at heterogeneous lists. And wrote two concatenation functions. I'd like now to point. Is the font size okay? I'd like now to point important difference between list and H-list. If you look at the parameters to those two types, for lists we put them on the left-hand side, while for H-list is on the right-hand side after the colon. So in list, A is called a parameter, while this list set is called an index. The difference is that lists are uniformly parameterizing a data type, while indices are intertwined with its structure. One way to see it is that in Agda you can specify that several definitions depend on something. So if I have, let's say, one function that depends on configuration and GHI, and another function that depends on a boolean, and that should something like this. Then instead of having all those functions taking a parameter, what I can do is I can say module, which takes a config, and in this case I will have this config as available as A in all three functions. Okay, so this allows to uniformly parameterize several functions as a module. And if you do it on a data type, so I can use, so I'll do this way. So I'll define a module list module, which will take a set. And in this case, I can write a list and a cons operation, which will be A to list to A to list to list. Okay. Okay. One. Now, if you compare it to the previous definition of lists, where did I have it? It's here. There is no A anywhere, except it's used where it's needed. So this is a parameter. So you can think of a parameter as something that can be extracted out of a data type to the module header. Another way of thinking about a data type is if your type can be written in Haskell 19.8 syntax. So data list 1 equals A equals nil or cons A list A. Then then every parameter, everything here is a parameter, and if you need the GADT syntax, you have an index somewhere. Also, notice that if you have a parameter, this A will scope uniformly over every constructor, and you have to write list A. I cannot say here list something else. For indices, they are not bound, and if I'd like to refer to this list set, I need to quantify over it. If I'd like to use this list module inside, for example, I'd like to write an append function, append list 1 to list 1 to list 1. Yeah, I won't define it properly. Then you can notice that I don't give any parameters to list 1 because it's fixed in the whole module. However, if I'd like to use this append function outside of list module or use the type, so I'd like to do something like list module dot list 1. Now I need to give it the parameter, as otherwise the compiler will complain. Okay, the same goes with the append.
Can we import a list module with this parameter and then use it without
open list module bool, I believe. And now, if I'd like to have yep, that works.
So we don't need to specify.
I don't. Yeah, I'm. So if you say open, you are opening the whole module. So it's like combining namespaces. Okay. The next point I'd like to mention is one of the most famous data types when it comes to generic programming, vectors. Vector 0. So a vector is a length indexed list, and despite the name, it has nothing to do with vector spaces. A second. So this is a list indexed by its type, by its length, and notice that we have both a parameter, which is A, so this vector, the constructors of vector are uniform in A, while the length of the vector is indexed. You might see other situations where you might see indexes are, you have terms and they are parameterized by their type, or you might see, they are indexed by the number of free variables, or you have functions and they are indexed by the number of operations they perform, and so on. Which one? Oh, is it broken?
No, no. Microphone? You don't use? No.
I just use this one.
It's okay?
Yes.
Okay, sorry.
Okay, let's write a few functions on vectors. Map. So if I try to write a map list function, list I to list P, and I case split on X, then Agda gives, I try to fill this automatically. You see, it's not the implementation I was thinking of. However, if I try to write map vector, not vector an this time the implementation that is filled in automatically is the one I was thinking of. So this is an example where giving out more specific types can help you in writing the correct program. Like types guide values instead of types being inferred from values.
What was wrong with the previous implementation?
The previous implementation looked like this. It just lost this X. But for vectors, this is type incorrect because map should preserve length. For lists, this is type correct. Okay, one more example is head, and for list there is no type safe head because the list can be empty. While for vectors,
I'm sorry, because you left the incorrect.
Yes.
But my question is, can we assume that if this map vector function would be like mapping in functor, fmap in functor, right?
Okay.
It wouldn't hold functor laws.
Why? So the thing is that
the wrong one. Right?
This is correct. So no, it would. It wouldn't be the implementation you think of, but it would. Yeah.
The wrong implementation, right?
So the wrong implementation would not because fmap ID wouldn't be ID, right? Yeah. Okay, head or you can notice when I ask Agda to case split on X, I don't even get the nil case. This is because the nil case is not compatible with this function signature. Okay. Another type I found pretty instructive is convert, and let's convert a set, a vector, to a pair of its length. Sorry, I wrote it right. Okay. From a list of A to a pair of NAT and vector A. So here we have a partial application of vector, and remember that pair takes first a set and then a function which takes a value of this type. So this is a pair of a natural number, which is followed by a vector of that of length, which is that number. So let's write one convert. Convert x equals question mark. I will case split on x. And for convert nil, it's pretty simple. We have 0 and then nil. But what about converting a non-empty list? What would you do here?
Call the recursive case?
Yes, we need to call the recursive case, and then you would need to case split on this. And while in Haskell you have case expressions, the issue with case expressions is that they are on the right hand side, they are an expression, but usually when you do dependent pattern matching, you would like to refine the arguments to the function. So the case expressions are done on the left hand side, and they can be used to determine which clause of the function to pick. While in Haskell, if you are on the right hand side, you cannot go back. Right? This is the difference between if statements and guards. So to do this, you can say with convert, and I will call this XS. You can repeat this. You can repeat the next line, pipe symbol, and give an extra variable. Okay. And now the goal is to have to write a pair of NAT and vector A. I'm sorry, I've done something wrong. Oh, we need now to case split on A. And the result will be, so A is now the length of the converted output, and x1 is the vector, and we need to const to it. So it will be stack A and x colon y. Okay. Oh, so this convert function, actually Agda cannot figure out the end because end shouldn't be there. Okay, so this is a conversion function. It goes from a list to a pair of natural number and a vector that is specifying, and a vector, essentially we are making, we are converting a list. So you can think of this as a list being converted to 1 plus a squared and so on. What about vector length? Vector an to NAT. How would you implement this?
Match on nil. First match on empty vector and returns 0.
Yeah, we could button match on the empty, like do it the same way we implement length for lists. where we return 0 for empty list and 1 plus the length of the tail. But since vectors already have their length in the type, we can return this length this way. Okay? So it's a bit funny because this function actually is ignoring the vector it's given. It's returning the implicit passed argument, which is inferred out from the context. And a variant of this idea is a type of function. So I'll give there an A as A, and I will return a set. Okay? So I can say type of and get this A, ignore the argument altogether, and return A. So the type of false is bool. What about a replicate function? So from A to vector an. So the goal here is that we have a natural number, we have a value, and we'd like a vector which has that value repeated n times.
So when this function is called, how will it infer the n?
Well, it will depend on the context, but it doesn't have to infer. I might specify the n, right?
But you are calling it implicit, right?
I can still specify it, right? And when I call it if this was an explicit argument, I also don't have to specify it if I use the underscore. So what will be here? The result? How to write replicate? We need to recurse over n. So I need to pattern match on n. And one pitfall is that if you write it this way, Agda will try to implicitly match on this A because that's the first implicit argument. So you can either do this, or you can say n equals n, and this means that the implicit argument n is bound to a variable called n. Okay, so I can now case split on n, and the case for 0 will be nil, and the case here will be x : replicate x, which looks a bit funny because in Haskell, if you wrote something like this, repeat x equals x : repeat x, that would be the infinite lists, but the implicit index is doing the job. So effectively, I could write it as this way as well, if I also specify it's n. Okay.
But it's implicit parameter.
Yes.
So you when you will call this function, you won't provide the argument, but you will provide this as expected type.
Yes. So I can say vector bool 5 x equals replicate false, and x is the vector you see on the bottom.
Brilliant.
Okay. Okay, what about vector concatenation? It looks pretty similar to list concatenation. So let's write it. Concat vector to vector A. And what will be the result type? If I add two vectors? n plus m. So concat vector uv equals question mark. And the implementation, in fact, turns out to be the same as for the list type, except, again, we can just tell Agda to automatically infer the missing call, because thanks to the length annotation, this time we will get what we wanted. Of course, it doesn't mean our implementation will be necessarily correct, because you can write a different function of this type, but in this case, it gives the simplest thing that works, which in this case is what we need. Okay, let's write a reverse function. And in fact, I will make this argument explicit. So let's case split on V. And we have two cases. If it's 0, well, it's nil. Oh, you might notice those dots. They mean that there is only one way that this argument can be filled, because this nil forces the natural number to be 0. Okay, so we'd like to reverse a vector which starts with x, and let's say we are fine with the quadratic algorithm. So how will that look?
Reverse V?
We definitely need to reverse V. Concat vector. And a second argument? Reverse. Actually, I should say reverse M V, right?
Reverse x, right? Shouldn't you reverse x?
No, it's just one element.
Oh, right.
Okay, so there will be one element, so it will be cons x nil, right? Did I write cons? No, I wrote double. Okay.
Why did you have to remove the dot?
Oh, because if you use the dot, you can this thing doesn't get a name. We got an error. The error is that m plus 1 is not equal to successor of m. Now, why is this the case? Didn't we define addition this way? Well, we defined it the other way around, right? It's defined as sac x plus y, and we have the case where we want m plus sac y, right? And Agda is not smart enough to deduce from this definition that those two things are the same. So one thing you might think of is, okay, so let's comment this out, and instead write x plus 0 equals x, and x plus sac y equals sac y, right? If recursion over the first argument doesn't work, let's go to the second argument. Unfortunately, then you get an error that m is not equal to 0 plus m in the earlier function of concatenation. Well, we concatenate by looking from the left on the left vector, and this previously agreed with the addition of numbers, but now it doesn't. So that's not the way to go. We need to concatenate before we can reverse vectors. So what's the problem here? We are looking at the problem of equality. And equality is much harder. There is something called judgmental equality. Judgmental equality is something that you can think of happens in the type checker. It means we are reducing the left-hand side and the right-hand side and comparing whether they are actually equal. For example, if I ask Agda to normalize something, like add 2, 3, I'll comment out. Okay. Plus 4. So 3 plus 4 is 7. This means that 3 plus 4 is judgmentally equal to 7. So the type checker can figure out the equality. However, m plus 1 is not judgmentally equal to sac m. So even though it might be equal to u, it's not equal to the type checker. And if you'd like to convince the type checker that some things that are not obviously equal are equal, then you need to use propositional equality. Also notice that while those two terms are not equal, for any specific m, they are judgmentally equal. So Agda can check that 3 plus 1 is equal to successor of 3. Agda can check that 100 plus 1 is equal to successor of 100. However, being able to check every specific case does not mean you are able to check it in general. So Agda can check, in fact, every natural number, but Agda can prove, for every natural number, Agda can prove that this equality holds. However, it doesn't mean it can prove that for every number this holds. Okay, that's the distinction. So what can you do in this case? You can define propositional equality. So this is a data type that reifies, meaning makes specific the identification between two things. So let's write this: equality set A to set okay. So this data type means that two of its arguments are equal. So let's write some function with this. For example, symmetry. So you can build a library with this. Just like when you have functions and you see that functions are first class, then you can build a library with functions like ID, composition, folding, and so on. For equality, is the same thing. Once it becomes a first class object, you can have complex APIs with it. And I will show you some parts of this. So let's try symmetry.
We just randomly cooked up a data type, right? So how will Lambda realize that this is the equality it needs for showing that these types are equal?
Those two equality sees that you see this x and this x are the same.
Okay.
So that's why it means they are equal. This is just a normal data type. I didn't say anything magic to Agda.
So why isn't this thing built in?
Once again?
Why don't we have a built-in notion of this?
There is one in the library, and it's better to have things in a library than built into language, right? And I am not importing a library because I'm not doing this in the world talk. I am building here the whole universe from scratch. So let's write a symmetry function. I have a set, I have x, y, and I know that x is equal to y, and I'd like to know that y is equal to x. Okay? So symmetry x, y, and this is my equality proof. Okay, so let's write this. Now, I have this equality proof, which tells me that x is equal to y. Well, therefore, y is equal to x, so I can just type refl. No. The thing is that you need to think about equality not as something that just happens. Instead, equality is something that requires evidence. And to use this evidence, you need to pattern match on egg. Okay? And only after you pattern match, only after you specify that you are looking at this equality, notice that Agda changes this second y to .x, and the goal, which previously was equality of yx, becomes now equality of xx. Likewise, for transitivity, question mark. If I try to write ref instantly, I will get an error that x is not equal to z. And in fact, you see that the goal is x equals z, and we have two pieces of evidence. Now, if I just use one of them, notice the goal x equal to z will change. Oh, it doesn't change, but still we now have a piece of evidence that the type of f has changed from y equals z to x equals z. So I can use it instantly. Or I could write refl equals refl, which might behave subtly different because this thing will always reduce if your first argument is known to be refl, and the other one requires both to be pattern matched. But this is rather a subtle difference. Okay. Another example will be a function commonly known as Cong. A is set, And this time I'll write the arguments implicit. So the way conc works is that you have a function between two sets, and if you know that x is equal to y, then you know that f of x is equal to f of y. So conc f, and the definition here actually follows the same pattern. Okay. So I pattern match on the equality proof, and thanks to it, the type of the expected value on the right hand side is refined, and I can just use referral. Here is another example. I can type unit test eq 2 plus 2 4. Unit test equals ref. And notice I effectively get a unit test that is run during compilation. Right? This function checks whether my plus function behaves correctly, and it does that during compilation.
Can I just ask something about the conc that's talking about type level equality or value level equality?
What's the difference?
What?
You need to think about types as first class values.
Okay.
So I can use eq for both types and values.
Okay.
Right? The whole premise is that I'm trying to show if you remove the barrier between types and values as it exists in Haskell, and allow types and values to be in the same namespace, to be types depend on values and values depend on types, you can get more stuff. So we...
Both. It's both.
Yes.
But for that we have to have set in inbuilt, right?
You need to have type in type, yes.
Yeah, is that a good thing? Is that a good thing?
I could talk about this, but it would complicate other stuff, and I'd like not to.
So can we check for equality between two functions?
Here is the thing: we are not checking anything. We are just asserting. I know what I have written, and I will get to this soon. We are not checking that things are equal. We are just asserting that they are equal based on their form. And so, let me write one eq add. Well, let me see that addition is the same thing as addition. Oh, sorry, I didn't add it. Call it add. I added plus. There you go. Okay. So, in fact, if you can write this type of thing or this type of thing when those two things are judgmentally equal. What you are getting is a propositional equality. However, you can assert that two things are equal when they are judgmentally equal. But what if they are not judgmentally equal? Like in this case of concat vector, we have m plus 1, and we all know that m plus 1 is equal to sac m. But we need to prove this to Agda. So let's do this now. I will call this sac lemma. And we need to prove that sac m is equal to m plus 1. I'll make m. So m is explicit. So let's case split out m.
So how is m plus 1 defined again?
M plus 1?
Yeah.
Well, that's the addition function I started with.
Okay.
So 1 plus m is by definition equal to sac m, but m plus 1 is not. Okay?
That is what we are proving.
Yes. So let's see. In the 0 case, our goal is to prove that 1 is equal to 1. Well, this is clear. What about this case? Our goal is to show that sac m is equal to sac of m plus 1. Do you have any ideas how to show this? In sac lemma m, yes, interesting. If we call recursively sac lemma m, then we'll obtain this value, right? So if I call sac lemma m, then we'll obtain we'll obtain this thing, right? That sag m is equal to m plus 1, but our goal is a bit different. We can use rewrite, yes. But I'd like you to notice that this is Conc. Right? We have this equality object, and if I use Conc sag on it, instead of knowing that A is equal to B, I will know that sag A is equal to sag B. And that type checks. So now we have proven that sag m is equal to m plus 1. Another way to write it is, if this was in a mathematical textbook, it would be for all m, like m prime or m plus 1 equals, m1 plus m equals m plus 1. Okay? So you can think of the for all quantifier, which starts mainly theorems, that this is true for any m, as a function which takes a value of this type and then returns evidence that this is correct. And we have proven that this is correct. You can also think of this as an inductive proof, where we have a case for 0 and successor, and we are using the case of case for the number below. And once we have this successor lemma, let's go back to reversing.
So you have tactics like rewrite?
There are tactics, and I will now show one. Recall that our goal is to we are blocked here because m plus 1 is not known to be sag m. What you can do is you can tell Agda to use this value as to rewrite the result type that we have here. And to do this, you can say rewrite sag lemma m, except there are two problems. One problem is that I need to move this reverse function below, because functions needs to be defined because this one depends on the other one. The other problem is the rewrite keyword requires that you tell Agda this is the notion of identity I'd like to use for the rewrite keyword, and to do that you can tell Agda built-in equality. Okay, and there you go, this type checks. So we now have a correct, although slow, definition of reverse.
So what is the non-tactic way to write this? What is the non-tactic way to write this?
Oh, if you wanted to do it this way, you could, for example, define a function that would convert, if you had equality evidence that x equals y, it would be a function from x to y. And you would call this function with sag lemma.
Is there any way for ACT to automatically find this sag lemma proof? And, I mean, any way that you don't have to use rewrite sag lemma m, so that it can automatically find a way to prove that these two things are equal?
I don't think there is one. Generally, like, this problem is undecidable. And if Agda can prove that those things are equal automatically, well, you have judgmental equality. So you could extend the judgmental equality, but you also want to keep the compiler simple. I think there might be some automatic tools for this, but I don't know about this. Okay.
So how do you actually do that? Like, you have the evidence that these two types are equal, and you go from this type to that. How do you do that?
What's that?
The thing that you just described.
Yes.
So how do you actually do that? That you say that if
Oh, so what you could, so if you don't want to use rewrite, so actually rewrite is syntactic sugar for a double width application. The way you could do that is you have this sag lemma. So sag lemma, using sag lemma, you could show a function that would take a vector of this length and return a vector of this length. So essentially a cast. And you could use this cast as a function here instead of rewrite.
But how do you write that function? Could you please
Well, you pattern match on this equality proof. Sac lemma vec. So we'd like to go from a vector A of length sac m to a vector A of length m plus 1, right? Sac lemma vec m v equals okay. So the goal here is now to convert this thing into this thing, and I can say with sac lemma m you also need to sac m.
What happened that you lost the syntax highlighting?
If you have a syntax error, you lose syntax highlighting, right? If I start a comment, okay, I'm not sure what exactly to use, but if you have an error, you will lose it. Anyway, that's how you write a sac lemma, and this is essentially what rewrite is rewritten to.
So why are there two bars again?
Because you would like to pattern match on this function, but Agda doesn't allow you to pattern match on reflexivity if it cannot just eliminate variables, because then it's not clear what it would mean. So you need to also to weave on this, match on this. Okay. I have one example I found pretty interesting. It's from a lecture by Conor McBride, I think. Suppose I define a natural number identity function. However, it will not be just NID x equals x. Instead, I will do something very similar. Okay? So this is also the identity function, but it might not be obviously so. Now, if I'd like to cast a vector of size n to a vector of size NID n, then Agda will complain that n is not judgmentally equal to NID n. Okay? However, what I could do is I could convert from this vector, from NID n to A. But this function works fine if I type it correctly, of course. Okay? So you can, however, convert from vector A NID n to vector A n, and you can also do this. But if you try to mix them, Agda will complain that NID n is not equal to n. It's not known to be equal. What you can do in this case is you can pattern match on n. And notice the patterns we are matching here correspond to patterns that are in the definition of NID. So often when you'd like to eliminate a function, that for example here, what you need to do is case split on all different you need to case split on all different clauses that are in the definition of this function.
So why does it work now?
Because NID of 0 and NID of sac n are judgmentally equal to 0 and sac n. Okay? Another example, let's define a not function. And let me show this. Suppose you have a boolean and you know that this boolean is true. Let's see that this boolean, that the negation of this boolean is false. Well, if you just pattern match on this equality, then this boolean becomes true, and I can just say here that this is refl. Simple enough. However, if I'm interested in the opposite direction, I'd like to start with not b equals false, b equaling false, and I'd like to show that b is true. It won't be that simple anymore, because I cannot run functions backwards. If I know that not b is false, then this I have to actually my left hand side has to be actually be not false and not true for me to be able to deduce that b is true. So what I can do is I can case split on b, and now I have two cases. One is my goal is to prove that false is equal to true. And I know that true is equal to false. I could use symmetry, or I could case split on this y and obtain this weird looking code. This means this is impossible, and in this case you don't even have to type the right hand side. Okay, so there is no way to put anything here, and this is an impossible pattern. As for forwards through y, this can be just ref, because we already know that b is true. We don't even need to pattern match on this y object.
So how did you realize that the first thing is impossible? The first thing is impossible because eq of true false is not possible. There is no constructor in equality that will allow you to construct a value of type eq true false.
It starts to look a little bit like prolog, like facts.
Those are facts, but I would say the essence of prolog is a bit different, right?
Yeah, sure.
Pattern matching is different, so on.
Can you remove this line?
Well, I can remove this line, but we will have incomplete pattern matching. Okay. So essentially, in some cases you don't need this line, but in some sense it needs to be obviously type incorrect. Okay. So this was about judgmental and propositional equality. I have another concept, and this will be decidable equality. So currently, so we had judgmental equality, which happens inside the type checker. We had propositional equality, which means we have evidence that we can pass between functions. Decidable equality is not when we are just asserting that two things are equal, but we are checking this. So to decide something means that we either say yes, and in this case I need a value of this type, or we say no, and in this case I need to reduce A to nothing, where nothing is defined this way. Break? Okay. Let's have a break. So let's continue. I finished at the notion of decidable equality. Let's define an empty set, and you can think of this as something being impossible, like equality between false and true. In fact, I can show that this empty set, empty type, implies everything, so absurd, from any type to void, from void to A. And the definition, if I try to pattern match on this X, Agda will say there is no such X. Okay. To decide a proposition means to say whether it's true or false. So this has two cases. Now, if you think this looks a bit asymmetric, that this is like A to void and this is just A, what you could write in principle is unit to A, right? Because unit to A is just A, so at least then it looks a bit symmetrical. But that's the normal way to write it. And let's write a decision procedure that will determine whether two booleans are the same. So this will be a decision procedure, that's bool, that will take two booleans and will decide whether b1 is equal to b2. So let's write this. 1, b2. I can case split, and in fact I can tell Agda to case split on both things at the same time. And the definition is, well, can be done automatically. The yes case is pretty simple. For the no case, we actually have to show the display a value of type false true to void, and we do this by empty pattern matching, just like we are. So it works the same way this did, except without, instead of void we have equality false and true. Okay, this was pretty simple, and it might remind you of Haskell's instance egg-bool. I will package this to a data type. It will be called this egg. So this egg will take a set and return a set. And to have decidable equality means to be able for any two values of this type to decide whether they are equal or not. Okay? And I can just call this this egg of bool. Okay? What about decision procedure for natural numbers? Well, again, we can case split on x and y. This case is simple, this case is simple, this case is simple. This one is a bit more involved. So we need now to check whether successor of x is equal to successor of y. So we call the knot xy. And we obtain a proof k, the result whether they are the same or not. And let's pattern match on it. If I get the yes, what then? So my goal is to show that successor of x is equal to successor of y, and I know x is equal to y. I can use conc, yes, but there is, I can essentially inline conc and pattern match on x1. So I case split x1 and I get only one case, which is revel. But now in my context, my goal is now to show that successor of x is equal to successor of x. Well, that's easy. Also notice that the left-hand side has changed. This is why why there is no case of. Instead, with is coupled to the left-hand side, because the result of this with can influence the left-hand side. Okay, for the no case, we need to show that we need to decide whether successor of x is equal to successor of y. What we know is that if x is equal to y, then we have a contradiction.
That we obtained from the lower level.
So, since we need to decide, the answer will be no. And now I can put a hole, and we are one step forward. So now we need to show that we know that equality of xy leads to empty case, and we need to show this, right? So since our goal is to write a function, let's write a lambda. Right, and this lambda will be from some function f to something. Okay, so now our goal is just to show that a contradiction, and what we know is that successor of x is equal to successor of y, and we know that if we know that x is equal to y, then we have a contradiction. So clearly we need to call this x1, right? Okay. So now we need to put here an x equals y object, while we have an object successor of x equals successor of y. If we pattern match on this, then then we'll get referral, and Agda knows that if successor of something, successor of f is equal to successor of g, then f equals g. Constructors are injective. So I case split on f, and you would think you would write it this way, referral, except Agda has two syntaxes for lambdas, and you can use the curly braces. Curly braces means allow you to have multiple clauses in lambda. So this is like a lambda case in Haskell. And once I have this referral, I can say referral here. Okay. So now we have a decision procedure for Boolean and natural number equality. What's nice about this, that unlike typing equality of NAT and equality of Booleans, we are sure this is correct, assuming Agda's this type system is correct. Right? So we have not only written a procedure, but actually it's proven correct. If it says it's equal, it actually returns a proof that those two terms are equal. If it returns no, it actually shows it actually gives a contradiction proof. Okay, what about this deciding equality of floats?
So what is something that is propositional equal but not decidable equal?
Propositional equal but not judgmental equal, you mean, or?
No, that we saw.
For example, functions. You cannot decide whether the arbitrary functions are equal, but you can decide. But given two specific functions, yes, you can say they are equal. For example, x equals x. Right? Propositional decidable equality is a property of a specific type, and propositional equality is a relation between two values of the same type. What about equality of floats? Well, this is just an aside. Floats have that funny thing that there is not a number, and not a number is not equal to not a number, and there is 0 and minus 0, and even though they are spelled differently and behave differently, they are equal. Right? So the solution here is that there are two operands that Agda provides, like built in, and one of them has this weird notion of equality that you will also find, say, in Haskell, and there is also another notion of equality which behaves sensibly, and in that notion not a number is equal to not a number, while 0 is not equal to minus 0. Okay, how about decidable equality for product? Recall that product is just the tuple type. How would that work?
So I have a question. So what can we do with decidable equality? I mean, can we write a function which takes a decidable equality for an arbitrary type and do something with it?
Well, one thing I can do is I can use it to determine equality, right? I can check whether 4 is equal to 5, and that replies, yes, it says it's not equal to 5. If I ask to decide whether 3 and 3 are equal, I guess yes, ref. Right? I can use it.
No, not in this trivial way, but anything non-trivial?
Well, let's try this. How can we decide this part? We'd like to decide whether two tuples are the same.
You should have decidability on the elements.
Right. So I need a mishat, and I need equality on A, and I need equality of B, and then I got decidable equality on product AB. Okay, so I got xy, I k-split on both. Sorry, I don't k-split, I need a p and q. I k-split on p and q. Now what? So I have two tuples, and I have two functions to compare those. Let me rename this. So this is decide A, decide B. This will be A1, this will be A2, this will be B1, and this will be B2.
Call dA on A1 and A2.
Yes, dA on D1 and D1 on A1 and A2, and I'll also call it on DB, B1, B2. Result 1, result 2, or maybe I got R and S. So I'll k-split on R. I got a yes, I'll k-split on S. Okay. What if, what in this case? Well, it will actually be pretty similar to the previous one. Oh, sorry, I'll maybe do it a bit slower.
Should you first say no?
Oh, I need to first say no. Yes. Yeah. So this works in a matter similar to natural number equality. No referral to extra. Okay. So we now have decidable equality on products. If this was Haskell, how would this look like?
Like nested case expressions.
Yes, what I meant is this. It would be an instance ec A, ec B to ec pairs. And in fact, if we forget about those proofs and just return booleans, I could just say A1 B1 equals A2 B2 is equal to A1 equals A2 and B1 equals B2, right? Is enough. Okay. What about the dependent pairs? Here I think there is something interesting. So our goal is to show a decidable equality of pair AB. And pair is defined this way. What will be the prerequisites for being able to decide whether two dependent pairs are the same?
Decidability on set.
We don't have decidability on set, but we don't need it. So remember, the dependent pairs are the pairs where the first element can be is arbitrary, an A, but the second element of the type of the second element of the tuple depends on the value of the first one. So if we'd like to compare those tuples, well, we will be first comparing the first element, and that's just decidable equality of A. Right? What about the second element? I cannot just say decidable equality B because this doesn't even type check. B is not a type, it's a function. What I need is this. Right? So this means to be able to decide whether two dependent pairs are the same, I need to first to be able to compare first elements, and for any possible value of the first element, I must be able to compare that to the type on the second component. Okay, so I have this decision procedure on the first element and the two. So on the first element, on the second element, and now I have two pairs. I will pattern match on them, and now what? I'll do with P A A1, right? Okay, so I case split on the result. If the first element in both tuples is the same, then I can use the decision procedure to compare second element, right? But if they are not the same, I cannot do this. As in previously, this was type correct. Previously, I could compare both elements in a single with stamped, but now to even be able to talk about equality on the second coordinate, I must know that the first coordinate is the same. So this means we have a nested with. Okay, and this will, and I'm in fact comparing using the decision procedure Q on A, right? Because I need to specify this A. Okay. If both are the same, okay, if both procedures say yes, well, I say just yes raffle, and otherwise this is all similar to this case. I can say no, and that will be lambda raffle to x raffle, and no raffle to x to raffle. Okay. So notice that with statements can form a tree, and this is a tree on the left hand side. So if it turns out that this pattern match, the function doesn't satisfy this match, it can go to the next one. Okay. Okay, I have a short story about the so type. So is defined this way. Okay. Notice this is an index. So you can, if you have so a value of type so x, you can pattern match on it, and this means that x will be true. Effectively, so is that's essentially the same thing as x as true equals something. This is an index. This is an index. If I really wanted to make it a parameter, well, I could do it by converting it to an this way. Eq be true to so b, right? Okay. You can use so effectively to clean up examples like the forwards one, and instead of saying this, you could say so be or so not be. The problem with so, however, is that it has no computational content. If you pattern match on it, yes, you learn that this predicate is true, However, it's extremely hard to extract any information from predicate. Like here we know that not B is false. However, this you cannot convert this to anything sensible. Instead, you need to pattern match on B separately and essentially rebuild the computation history of not. So, in generally, independent typing, you try to avoid data types like so. Sometimes you might use them, and instead create data types which contain information. One example is a view. I will show you a view, the parity view. So if you have a parity of k, then you can pattern match on it, and you will know whether k is of this form or of this form. Now, having parity by itself is not that useful, but what you need is a decidable parity. Yet you know that the parity of numbers is decidable. So you need a covering function, parity from k naught to parity k. Okay, I will not write it here, but I'd like to note that once you have it, and you'd like to write a function from natural number to natural number, phone parity, and what you can do is you can normally when you pattern match on n, you would learn whether n is 0 or suck. But what if you'd like to know, for example, go not through the unary representation, but through the binary representation of a number? What you can do is you can say then with parity of n, with parity of n, k split on a and I'm sorry, those shouldn't be implicit. And you got two cases, while the argument is refined to one of those two forms. So this allows you to create new induction principles, new way to deconstruct a data type different than the ones you got from the data declaration. This pattern is called a view. And for more, you can look at the paper called A View from the Left, I believe. Okay, I'd like to talk about constructivity for the moment. You might have noticed that, I'm sorry, I need to backtrack. One thing I wanted to give, one other example wanted to go with is, suppose you'd like to model a theorem that for every prime number there is a greater number. The way you could do that is something like this. Euclid Theorem. So for every number, we would like to know that there is a prime number that is greater than that. What you can say in this case is something like this. We have a natural number, and for every natural number, we return a dependent pair. This is the value of this pair, and this is a proof that this number satisfies the conditions. So it's a proof that this number is greater and that it's prime. So this way you could write your proofs. And another way to look at this is that the dependent product means for every natural number, while the pair means exists, like an existential type or the exists quantifier. So this means that for every natural number there is a number a such that this holds. So this way you can translate assertions And in fact, do I have this anywhere? So this is some random paper. It doesn't matter what is it about. What I found interesting is that so papers have those structure when they have some lemmas and definitions and so on. So this has definition 1, definition 2, and one thing I found interesting is this header, imported theorem 1, right? So it makes you think that those papers are libraries and one paper is importing the other. And that theorem is just a value, just like you are importing a normal function from a library, they are importing a theorem. But if you think of theorems as as values like that, it's not that weird. Okay. I'd like to speak about non-constructivity.
Can you write the body of the function of Euclid Theorem?
No. If you gave me enough time, yes, I could. But I didn't want to do it here. So I'd like to talk a few words about constructivity. And I will start with a pretty famous non-constructive proof. And the proof is that there is an irrational number with there's a power of an irrational number to an irrational exponent that may be rational. Okay, so there are numbers a, b such that a to power of b is rational, while a and b are irrational. And to prove this, there are two cases. Square root of 2 to power of square root of 2 is either rational or irrational. Right? It must be one of those two. If it's rational, our statement is proved because you have this power. And if it's irrational, this equality proves our statement. So it's a pretty clever proof, and I thought, can I model it in Agda? Now, I won't be writing like a full real number library. Instead, I just wanted to take the piece that's non-constructive and extract it. So I wrote it here. So this is the EC type, font. So let's go from the start. This is the normal EC type, except it's given a different name, so that will look more like equality. Now I'm defining postulates. Postulates allow you to say that something is true without giving an implementation. If you use postulates, well, you won't be able to compile a program to something that you'll be able to run, unless you say that a postulate compiles to something like an exception or something like that. And the postulates that are used in this proof are there is those rational numbers set, you can compute square roots, there is number 2, there is exponentiation, a number can be rational, the square root of 2 is irrational, so you have this, and 2 is rational, and you have this arithmetic fact. Okay? So, and the magic theorem I'd like to show is that there are numbers a, b, which are both irrational, but their power is rational. So how to do this? Well, this proof has those two cases, that it's either rational or irrational. So let me call this assumption. The assumption is that square root of 2 to the power of square root of 2 is rational. Okay? Sorry, that will be equals. So we have this assumption, and let's prove the magic theorem if the assumption is true. So that's case 1. In this case, we have two irrational numbers, and by our assumption, their power is rational. So we can just say n squared 2 Oh, and I actually need to have assumption. Yeah. That's what I was missing. Will be X. Okay, so that's case 1. And case 2 is that if it's irrational, then we have this part to this fact is 2. So case 2 is if assumption is false, so in this case it will be square root of 2 to the power of square root of 2. Okay, so that was like the boring part. What we have shown is that if the assumption is true, then we have the magic theorem, and if the assumption is false, then we also have the magic theorem. Okay? The problem is now, can we obtain the magic theorem? And the answer is no, because if we had a value of this type, we could pattern match it and learn what are A and B. However, this proof does not tell us what are A and B are. It's just it tells us in this case it will be that value, and in this case it will be that value. What we can do is we can combine case 1 and case 2 using the either type. So I can type case both, either assumption or assumption to void, to magic theorem. And in fact, I will introduce a synonym. Negation will be X to void. Case both. So in the left case, if we know the assumption is true, we just use case 1. And if it's false, we use case 2. So we just now need to produce a value of this type. And we cannot. However, what we can do, we cannot show that this theorem is true. But what we can do is show that it's not false. And I will show that it is not true that this assumption holds. Okay, and how do you do this? Well, Agda is smart enough to figure it out. And what does this mean? This double negations are continuations, and while it's hard to yes, it type checks, and you could check that it type checks, but I'd like to give you an analogy. Suppose you need to show this, either assumption or negation of assumption. Well, then you are stuck, because you don't know what to show. However, suppose I allow you to travel back in time. Okay? What you can do is then you can make this happen actually. What you do is you say, no, it's not true. And then someone will come to you eventually, if you are wrong, with showing, hey, this is true, now produce me a contradiction. And you won't be able to do anything. But once you are given that evidence that the assumption is true, you can go back in time and change your claim that this branch was true to this branch was true, because then you will have the evidence. So with time travel, you can actually show that this is true. And in a sense, the continuation monad is the time travel monad. Okay? And in fact, if you write, so we can also write fmap for this. Fmap is A, B set, A to B to neg of neg A, neg B. Fmap of f, x equals, and again, Agla can figure this out. But this is just fmap for continuations. And now if I have this, I can say that my theorem is not false. This is simply fmap of case both over M. Oh wait, magic theorem, not false. Okay, so this is constructive logic. If you don't think of things being true or false, if you think of booleans, for booleans, false and true are symmetric. You can just negate it. You can negate a false value to get true, and the other way around. However, in constructive logic, if you'd like to show something, you actually need to show an evidence for something. While if you'd like to show that something is not true, you show a function that takes a value and produces a contradiction. But showing that you have a negation of something is a weaker statement. You can just write a contradiction. Okay. Now you might be thinking, okay, I have a statement, I can negate it. I can negate it negation. What about the triple negation? And it turns out that triple negation is the same thing as the tower doesn't go infinitely. This is the same as a single negation. So while zero of negation and double negation are not the same, this one negation and three negations are the same. And the way you can see this is that, well, there is return. From x you can get to negation of x. Okay, so this is just return. Now if I substitute as x negation of x, then I have this. And on the other hand, if I have this and I negate both sides, well, negation changes the direction, so I will go this way. So as you see, they are both equivalent. So triple negation is equivalent to single negation, even though double negation is not equivalent to not negating at all. Okay. Also, what you can do is you can postulate that double negation is true, or that law of excluded middle, which means either something is true or false, is true. And we have shown this in the case of equality, right? We have shown that two numbers, for example, two natural numbers or two booleans or two pairs are either equal or not equal. So we have shown like excluded middle for being able to decide for some equality of some types.
Is it related to the things that Carter did it in his talk? Or
I don't think it is, but I did not attend his talk.
What we did, like, can't we think of this double negation as the dual of true in linear logic?
So there is no linear logic here because I am allowing to have things multiple times. Right? I am allowing to duplicate things.
Right. But like, are they related?
To which part?
Like this notion of the dual of true, which is not exactly true.
I'm not sure. Okay. Okay, I have one more thing to show, and those are recursors. Remember that I have shown. Remember that many list functions can be written as a fold. The issue is that this. Remember that when I was showing the dollar function, it was initially working only for non-dependent functions, and I had to generalize it. Many functions on lists can be written using folds. A function on natural numbers can be written by case splitting on 0 and successor. And it turns out there is a pattern for those things. So this is like the general iterate function. This way you can iterate a number. You start here and you iterate. You do iterate this operation n times. So in this case, I can just say z, and in this case, I can say s iterate as z as n. So, okay. So this is the general way you can write a function that does recursion on 0 and successor. In another flavor, if you'd like to write any function that takes a pair, well, this is uncarry, right? Uncarry allows you to write any function that takes a pair, a, b to c. And to do this, you supply a function of type a to c and b to c. Okay. So a to b to c. Okay. So those things are a general pattern called iterators, and they allow you to extract the recursion pattern in data types. However, they are done on non-dependent functions. This function iterate has a dependently typed version, and this is how it will look. Instead of A being a general set, so notice that when you iterate, you are iterating over the same set all over time. A is fixed. What recursor allows you is to vary the set you are iterating on with the natural number. So A will be 0, and in a step you can change n from an to a of sec n. Okay. Okay, I won't be trying to debug this. I have some silly mistake somewhere. My point here is that unlike iterate, in recursor you can have a different set for every number. So if you'd like to iterate a function, for example, whose type changes, let's say it goes from x to f of x, then you cannot do this using iterate, but you can you do it using recursor, and then you will get, for example, f of f of f of something. This is a general pattern that allows you to write any recursive function. You can also think of it as induction. You are showing that something is true for 0, and you are showing that if something is true for n, then it's true for the successor of n.
So you could use recursor to like clean up a lot of inductive proofs.
Yes. You can use it. In fact, if you have recursor, you don't need pattern matching. You can just use normal lambdas that don't pattern match, and you will have the same expressivity.
Which recursion scheme is that? That's
Kata.
Kata, right?
Yeah.
Is that Kata with type level then? Something like that?
Well, the thing is that normal kata is like iterate, right? But here we have a dependent kata which has a general which can be parameterized, and you can try doing this on the vectors, on essentially any data type that I have covered until this time.
So recursors are just eliminators for.
Yes. I should have called it eliminators, but yes. So this is a general way you can write any dependent function that takes a natural number. Okay, this concludes, I think, what I wanted to say. However, I have references.
Could you please upload this code?
Yes, I will. As for references, I've learned a lot from video lectures that you have links there. And there is a pretty nice book about AGDA, Verified Functional Programming. There is a book about Idris. And there is a lot about state machines, if you are into this thing. There is the homotopy type theory book. Homotopy type theory is about exploring equality. I didn't do this, but it turns out that you can have, just like you can have functions that take functions, you can have equality between equalities, and this has a lot of non-trivial structure, and there is a lot of connections to other things. And you don't need to worry that much about mathematics. The first 2 chapters are extremely accessible and a very nice introduction to the meta theory that's behind AGDA. There are many AGDA tutorials, and what I did, I was switching between those two a lot and learning a bit from every one of those. For protocols, this paper, Fun with type functions, is a non-dependently type version, but it also shown. I will put this on the channel. This paper is a non-dependently type version of protocols. But for dependent type versions, you can check session types and control ST in Idris. Finally, for constructive and non-constructive reasoning, you can check 5 stages of accepting constructive mathematics. It's a nice introduction how constructive reasoning, which is what I was doing in AGDA all the time, is different from non-constructive reasoning, which you might be used to. Okay, that concludes the talk. Thanks.